In this lecture, we're going to talk about context-free languages and pushdown automata. I want to start by just reflecting, where have we been, where are we going, and where are we right now? So we spent a huge amount of time on regular languages, right? And at this point, you should be comfortable with regular languages represented as a set, as a regular expression, as a DFA, as an NFA, and as a regular grammar. And we've also proven that some languages that are not regular, right? So we know there are some languages that are not regular. Those are languages that we can't represent with a regular expression. We can't draw an NFA for. So we're suddenly taking a big jump, and we're moving on to the next level. And we spent so much time on regular languages so that we could do everything in kind of really nitty-gritty detail on the simplest kind of language, so that you understand all the basics of the material that we're covering. And now we're moving on to the next level, okay? And now what we're going to do is we're going to talk about other kinds of languages. And we're going to do a lot of the same things that we did for regular languages, but I get to move a lot faster as I teach you for these things, because now you understand the idea of how a language can be a set and a regular expression and a DFA and an NFA and the equivalents and whatnot. So similarly, as we move on to the more complex kinds of languages, we will see that they have lots of different representations too. Okay, so what we're going to do now, because you have all these skills that we've built up over the semester, is we're going to talk about and we are going to prove things about much more complicated languages. And we're going to realize it's not so hard to do because we have such a good foundation in this material. Okay, so now we're going to talk about this new kind of language. We've been talking about regular languages, remember, forever. And now we're going to talk about languages that are context-free languages. Okay, so just to review, we've already shown that some languages, for example, A to the N, B to the N, where N is greater than or equal to 0, is not regular. How did we show that? We used the pumping lemma, right? Well, actually, what we did was we did a proof by contradiction that took advantage of the pumping lemma to help us find a contradiction, right? Now, we know that we can represent this A to the N, B to the N using a grammar, right? If you remember when we started learning about grammars, the first thing we did was we learned about grammars that were just generic grammars, not regular grammars, right? But just generic grammars. So we could write something like S goes to ASB or lambda, right? And that will generate this language. This is not a regular grammar, right? We know that because there's this non-terminal right in the middle there. But it is a grammar, right? So a couple of weeks ago when we talked about grammars, we learned the term context-free grammar and the definition of a context-free grammar, right? And a context-free grammar is a grammar whose productions are of the form S goes to omega, where S is a non-terminal, so we only have one non-terminal on the left-hand side. And omega can be any string over the alphabet of terminals and non-terminals, right? So this is the kind of non-regular grammars. Remember, we talked about regular grammars versus context-free grammars before. And so we're just back into the world of context-free grammars because we're moving beyond regular languages. So here is my context-free grammar for A to the N, B to the N, right? It's what I wrote before, because of course you remember, I shouldn't use a double arrow because that means something in context-free grammars, right? Or in grammars in general. You remember that this expression here is really two rules just with a shortcut, right? So this is really one rule, S goes to lambda, and another rule, S goes to ASB, which is what I wrote before. I wrote them in a different order, but it's fine. So question one, is this a context-free grammar? You bet, right? It's got, on the left-hand side of all our production rules, they all have just a single non-terminal. And on the right-hand side, we have a string of terminals and non-terminals. That's fine. So, yep, it's a context-free grammar. And the next question is, are all regular grammars context-free grammars? And I hope that you will recognize already that, yes, regular grammars are a subset of context-free grammars, but all regular grammars are therefore context-free grammars. Not all context-free grammars are regular, right? I mean, this is not a regular grammar right here. Okay, this is just context-free. It's not regular, right? Because we have this non-terminal in the middle of a production rule on the right-hand side. But it's context-free, and if we take any regular grammar, that's also a context-free grammar. So yes, all regular grammars are indeed context-free grammars. Just like we have regular grammars and how they relate to regular languages, context-free grammars relate to a certain type of languages that are called context-free languages. And here what we're going to say is a language is a context-free language if it's generated by a context-free grammar. So if you can make a grammar for it that's a context-free grammar, then the language that that grammar generates is a context-free language. So again, here's a question. Are all regular languages context-free? And the answer is that yes, of course, all regular languages are indeed also context-free languages. Let's talk about why that is. Well, what is a regular language? Well, one way to say what a regular language is it's something that's generated by a regular grammar, right? If you have a regular grammar, then we know there's a regular language that corresponds to it, right? But if there's a regular grammar that corresponds to that regular language, then you could also generate it with a context-free grammar, because whatever this grammar is, the regular grammar is, it's by definition context-free, because all regular grammars are also context-free. But if you can generate it by a context-free grammar, that means that it is a context-free language, by our definition of what a context-free language is, right? Context-free language is one that's generated by a context-free grammar. Beautiful. So when we talked about regular grammars, we talked about what if you want to take the union of two regular languages that you happen to have two grammars for. How would you combine those grammars so that you get the grammar for the language that's the combination of the two? And it was a little tricky at times because we had to make sure that the new grammar that we generated was always regular. But in the case of context-free, it's really, really easy. So let's suppose that M is a context-free language, and that M's context-free grammar starts with the symbol A. So we're not using S, we're going to use A. And suppose that the letter N is another context-free language. And let's make sure that all of our non-terminals in N are different from the non-terminals in M, right? So that just says we use different capital letters for the two grammars. Easy enough. All right. And let's say that instead of using S for the start symbol for N's context-free grammar, we decide that we're going to use B just because we can, right? And furthermore, we're going to assume that S is some non-terminal that we haven't used in M or in N, right? Again, it's a non-terminal. We can use whatever the heck capital letter we want, okay? So if we want the context-free language that is represented by the union of those two context-free languages, right? I'll tell you it is also a context-free language, right? Taking the union of two context-free languages probably seems expected. You probably expected it would be context-free, and in fact, yep, you're right. And how do you do that? Well, if you have one context-free language that starts with A, goes to whatever it is, and you have another context-free grammar that starts with A, another context-free grammar that starts with B, goes to whatever it is, right? If you want to, so here's one context-free grammar, and here's another one, and there's a whole bunch of rules in here potentially, and a whole bunch of rules in here. And what we said is because of the things that we've written here, there's no non-terminals that these guys have in common. Okay, so we can just take the union of that very easily by saying, all right, list all the rules for this first grammar, list all the rules for this second grammar, and add one more rule at the very top with a new start symbol that says S goes to A or B. So now, of course, you can follow either path. You can follow the A path to generate a string or the B path to generate a string, and you end up with M union N. Okay, and if we look at the language that is created by concatenating the language M in front of the language N, so we take one string from M, we concatenate it with one string of N, and the set of all those squished together languages is a new language, right? If M and N are each individually context-free languages, then, as you would expect, the concatenation of the two languages is context-free. And again, if we have, rule 1 that says A goes to, or excuse me, grammar 1 that says A goes to whatever, and then we've got a bunch of rules, and we have grammar 2 that says B goes to whatever, and then there's a bunch more rules. If we just create a new start symbol and we say S, our start symbol, goes to AB, and we take all these rules together, now we have a context-free grammar for the concatenated language represented by M and N. And this is something we couldn't do with our regular grammars, right? We couldn't have a rule like this one in our, when we were looking at regular grammars and we were looking at concatenation, because of course you can't have two non-terminals on the right-hand side in a regular grammar. But in a context-free grammar, it's fair game, so we're in good shape. And you'll find that the last rule for star is equally straightforward. If you already have a language M, right? So our language M, if you look at its grammar, it starts with A, and then there's all the rules, right? Then if we want to figure out what is M star, what's a grammar for that, you just create a new start symbol S, which goes to either AS, so as many copies of you as you want of this first rule here, right? Or lambda when you're ready to end. So this is very, very similar to when we combined regular grammars. If you if this slide has been the least bit tricky for you, go back to where we talked about regular grammars and go back and take a look at the piece of the lecture on how we combine regular grammars together to get a new grammar. The big takeaway from this slide, of course, is if you have two context-free languages, you can take the union of them, you can take the concatenation of them, or you can even star one of them, and the result is still a context-free language. So here's some problems that I got out of the previous edition of the book. I couldn't actually find anything quite like this in our current book in this chapter, but it's still useful to practice. It's problems we've more or less done before, but let's do them again just for review. So the first one here asks us to find a context-free grammar for the language A to the N, B to the N plus 2 for N greater than or equal to 0. So let's just take this and stick it up here in the corner, and I will write the language down here so that you can see what we're trying to do. So we're doing A to the N, B to the N plus 2, such that N is greater than or equal to 0. Right, that's the language we're trying to create a grammar for, right? And, what does this mean? This just means that every time, every string in our language has 2 more letter B's than it does A's, right? And so this is pretty straightforward, right? One way to do this is say, okay, I'm going to have my start symbol is going to go to A followed by two little b's. So we add those extra b's right away. And then we deal with the A to the N, B to the N part. So we'll say A goes to, remember we need to have it kind of grow outwards because we need the number of A's to match the number of B's and spread outwards. So we'll say A goes to AAB or lambda. Easy enough. All right, so let's see, can I squish that a little bit? So the next one says palindromes of odd length, right? And again, it's a language that we've done before, right? The first and last letter has to match, and all the intermediate letters have to match. So this is really very easy for our palindromes. We want something like this. Our start symbol, well, every time we can either have an A at the front with an A at the back, so we're growing outwards again, right? So we put an A at the front of the back, or, and I'm just going to do it on another line because I seem to have run out of space, we could have a B at the front and a B at the back. Or, since we want odd numbered palindromes of odd length, we need eventually not to end with a lambda, but to end with one more letter so that we finish. So I'll just say that my final thing is you could also go to an A or a B, right? So this is 4 rules written on 1, 2, 3 lines, as opposed to this piece up here, which was 3 rules written, I guess, on 2 lines, right? Okay, so let me squidge this one out of the way. And we'll do one more. I don't know if you can read this. The last one we need to do for the first problem is just all strings with the same number of A's and B's. So that's interesting because now it's not a palindrome per se. It's just we have the same number of A's as we do B's. So there's all sorts of ways that we could do this. So let's squidge that back down. So, you know, we can't do something like this one that we've done before because we need to allow the A's and B's to come in any order, right? So let me tell you how I think about this one. If we already have a string, right, or if we're trying to generate a string, one thing that we could do is we could put an A and a B right at the front of any string that we already have. Or we could put BA at the front of whatever string we have. But we might not want to add to the front of the string right now. We might want to add to the end of the string. So we could also say put an AB at the end of the string. And we could also put a BA at the end of the string. But so far we've only put the A's and B's next to each other, and maybe we want a string that has 5 A's followed by 5 B's. So the last thing that we need to do is we need to say, all right, well, what if I put an A at the front and a B at the end, or a B at the front and an A at the end? And that's all well and good, absolutely. Actually, though, the final thing I need to do is somehow have a way for this to end, right? So I'll just throw in a lambda. So again, just for convenience sake, I've put 2 rules on the same line in several places. But, you know, you could have all of this actually on one line. You could have it spread out on 7 lines. It just kind of depends what's most convenient for you at any given time. Okay, so let's squidge that down. That's always fun. Let's bring this guy up again. All right, so now it says find a context-free grammar for each of the following languages. Now see, look at this one here. This one is 2 languages concatenated with each other, right? So we're starting with A to the N, B to the N, and concatenating that with A to the N, B to the 2N. So this is 1A and 1B, right? So same number of A's and B's, I'm sorry. And this is twice as many B's as A's. And all the A's come first in here and then the B's. All the A's come first in here and then the B's. And so what I'm going to do is I'm just going to use that trick that we talked about in a recent slide. I'll make a context-free grammar for each of those, and then I will concatenate them together. So let me just move these things way out of the way. shrink them super tiny so we have a little bit more room to work. Okay. So first I'm going to do my grammar for a to the n, b to the n. And maybe I won't start with s, I'll start with a for a change. So I'm going to say a goes to AAB or lambda, right? That gives me a to the n, b to the n, the same number of a's as b's. And then I want another grammar that maybe I will start with a b that goes to, that gives me 2 b's for every a. So that is a, b, and 2 little b's, or lambda. And to make this the concatenation of the two, I just create a start rule that looks like that. And magic, this is the language that that we saw in here, right? This is these two languages concatenated together, right here. Terrific. The second one it asks us to do, before I shrink this down again, is just a to the n, b to the m, where n is bigger than m. So we always have more a's than b's, but we don't know how many more. Okay? So let me do some rearranging here. Let me shrink this down a bit. Let me take this purple guy and put it out of the way. So now we're trying to do a language, remember, that has an arbitrary number of a's and b's. We just got to make sure that we always have more a's than b's. Okay? Or equal. It could be equal. Okay? So what I'm going to do is I am going to do a to the n, b to the n, our standard old favorite language where I do something like s goes to a, s, b, right? And this is going to give us a language that has the same number of a's and b's. And then what I'm going to do is I'm going to give myself an out, and I'm going to say, or you can jump to this other thing. So once you've got a string that has as many a's as b's, so you have the same number of a's and b's, then we'll go to this new production rule. And this new production rule is going to add as many more a's as you want. So I'm going to say b goes to ab, or lambda. And if you take a look at this language, I think you'll see that what you get is you start out by coming up with as many, as many a's as you have b's, and then you add as many more a's as you want on there. So, pretty good. So, being so familiar with regular languages and regular grammars and whatnot, you may have the following question. All right, regular grammars were fun, but the thing that I really liked about regular languages was being able to draw NFAs and DFAs, right? Because that, for a lot of people, students and faculty, that just seems much more intuitive if you're just drawing it out, right? If you draw it as a machine, it's some sort of an automaton. And so perhaps you have the question, is there a machine that we can use to represent a context-free language, right? I can deal with these grammars, but I'd really like to see a machine. And, I mean, you probably guessed the punchline here. I probably wouldn't have asked the question had there not been one. Yes, there is. The machine is called a pushdown automaton. Now, pushdown automata, right, singular automaton, multiple automata, are actually very, very similar to NFAs. And what is a pushdown automaton? Well, it's essentially an NFA with a stack. So I imagine for most of you this is review, but maybe not for everybody. So a stack is a data structure that has 3 different operations that you can do on it. And what I should say is lots of people have lots of different variations on the interface for a stack with what the built-in functionality of a stack is. These are the operations we're going to use for our class. So if you have a stack, you can push a value onto the stack, you can pop a value off of the stack, or you can do a no-op, which just means do nothing. Now, what does this mean? Well, ignore this picture for a minute. We'll get back to the picture in a minute. The classic stack example that is given to people if you are not familiar with stacks is that of a stack that's found in a dining hall, a stack of dishes. So you can imagine in some dining services or whatever, they have this kind of magical box thing that holds plates. And it's made so that at any given time you can only see a single dinner plate on the very top. And there's some kind of a spring in here, and there's a whole bunch of plates stacked up on top of each other. These are all supposed to be plates, one on top of the other. Whereas this thing down at the bottom is a spring. You did not take this class for my artistic ability. Anyway, and what happens is if you take this top plate, right, and you remove it from the stack, then the spring is weighted so perfectly that it pushes up a little bit and reveals the next plate, so that at any given time there's only one plate visible on the top of this stack of plates. And if you pile a few more plates on top, they will all kind of push, the weight of them will push it down because it's such a perfectly balanced spring, so you only see one plate on top. So if we get rid of all these beautiful drawings for a minute, here's the kind of stack we're going to use in class, this thing. And I'll draw it like this. It sort of looks like a better version of the dining service stack. But this is a stack that has three items on it. At the very bottom of the stack there's an X, then there is a B, and then at the top of the stack there's an A. So if I say push some value on this stack, for example, suppose I push another B, then what happens is that B gets added to the top of the stack. And if now I push a C, that C gets added to the top of the stack. And if I say do a no-op, then nothing happens. But if I say pop, what happens is this top value, whatever's the top value on the stack, in this case the C, is returned. It's taken off of the stack and it's returned as the value from the method. So if I do this pop, it's going to return a C, and if I do another pop, it'll return that B. That's essentially a stack. So a PDA, a pushdown automaton, I said, is an NFA, but the NFA, in addition to getting all the content that your standard NFA gets, we also get this bonus stack. And it's amazing how, just given a stack, we can suddenly go from only recognizing regular languages to recognizing context-free ones. So let me explain the notation we're going to use to you. And it will all make sense in 1 minute. Bear with me for a minute, okay? Because I need to kind of show you the notation, show you the PDA, give you an example, and then all of a sudden everything will make sense. So bear with me for a minute and just kind of listen and pay attention. Watch this until we get to the example, watch the example, and then rewind right back to this point and watch this section of the lecture again, because I think that'll really help. Okay? So for our PDA, we have things that look very, very much like what we had as transitions in our NFAs. We still have states, so this is a state labeled A, and there's another state labeled B. And the thing that's a little bit weird is that we have, instead of just having a single symbol written on top of the arrow representing that transition, we have this kind of weird, this weird notation. And the weird notation, if we have, right here we have L, comma S, and it's sort of divided by O, right? And this says, if you're already at state A, and you see the letter L is the next letter to process, ignore what it says in the notation below here for a second about lambda, we'll get to that in a minute. But if you see the letter L, so you're at state A, and L is the next letter to process, and furthermore, whatever this S is what you see at the top of your stack, then you can do whatever O says. O is going to be a stack operation, and transition to state B. okay? And you use up that letter L in the process. So let's keep going, and it will all become clear what's going on here. So here's our classic example. This is a PDA that actually recognizes the language A to the N, B to the N, okay? And we have a stack here. So we have what looks sort of like an NFA, except that the transitions have these weird triple labels, right? And off to the side we have our stack. And one thing that we're going to do is we're always, before we start running anything on our PDA, we're always going to start with an X on the bottom of the stack. And we do that so that we know essentially when the stack is sort of empty, right? We can look at the top of the stack, and if the X is on the top of the stack, then we know that there's nothing left to pull off. And we just use X as a special symbol for our stack. Okay. So here's what we're going to do. Here's sort of how this works. Let me explain it to you in English, and then we'll look in detail at the PDA. What we're going to do is we are going to go through our string. So let me just shrink this just a little bit and move it up here. Okay. What we're going to do is, let's suppose that our string is the string A, B, 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 and that's what we're trying to do. Okay. What I want to do is I'm going to use my stack. Here's my stack, and I start with an X. And what I'm going to do is every single time I see an A, I'm going to kind of process it, and I'm going to add a Y to the stack. So there's another A, I add a Y to my stack. There's another A, I'm going to add another Y to my stack. And as soon as I start seeing B's, instead of putting things on my stack, I'm going to pop things off. So if I see a B, I make sure there's a Y at the top of the stack, and then I pop it off. If I see a B, I make sure there's a Y at the top of the stack, and I pop it off. If I see a B, make sure there's a Y at the top of the stack, and I pop it off. Now, if I have exactly the same number of A's and B's, then I will push the right number of Y's on the stack and then pop off that number again, so that when I'm done, I'll see the letter X. You with me? Right? If I have more A's than B's, then when I'm done, I'll see a Y left over on the stack, and that'll tell me, oh, you have more A's than B's. That's not in my language, right? If, on the other hand, I have more B's than A's, then I will get to a point where I'll be looking, I'll see a B, like suppose I have A, B, B, right? I will see the A, let's do it again, and I will push a Y on the stack. So that's a Y. And then I'll see a B, and I'll say, oh yeah, there's a Y, and I'll get rid of that one. And I'll see this other B, and I'll say, oh no, there's no more Y's left on the stack. I guess I don't have the same number of A's and B's. Okay. So now let's actually look in detail at the machine that we've got here at our PDA and see how it works. So let me get rid of this mess and pull this out so you can see it better. Okay. So when we start, right, we start processing our A's, right? So if we have, you know, suppose we have the string 1, 2, A, 3, 4 A's, and let's do another one that works. Okay, 4 A's and 4 B's. We're going to start out, and of course we start out, when we start the PDA, the first thing we do is we put an X on the bottom of the stack. So when we start, the first thing we want to do is push Y's onto that stack. And we have two options here at state 0, right? The first time we see an A, there's going to be an X on the stack, right? And so under that circumstance, we want to push a Y, right? After that first A, then there's going to be Y's at the top of the stack, right? Because remember, this says if you see this letter and you see that symbol at the top of the stack, then you do this thing. So after let's process the first A. So what do we got here? We are at our start, and we see an A, and we look at our stack, and we say there's an X on the top of the stack. So that means that we're running this. So I see an A, X at the top of the stack. So we're going to take that loop, and we're going to push a Y, because that's what it tells us to do. So we push a Y on our stack. and we say that A is processed. With the next A, of course, now at the top of the stack we see a Y. So now we need to use this other loop, right? If you see an A and there's a Y at the top of the stack, push a Y. So we push a Y. I'm sorry my X's and Y's are not looking more distinct today for some reason. Okay, we see another A. We have a Y at the top of the stack, so we follow this loop again. Get rid of the A, we push the Y. We see another A. My goodness, that's nasty. There we go, that's much better. Y. Another A, another Y at the top of the stack. We follow this loop again. So we push another Y. So now we have 4 Y's and an X on our stack, right? At this point, we see a B, right? Now we have 2 options here. One option is we can, if we see a B and there's a Y at the top of the stack, we can pop. And that's actually the option we're going to take. That's what we're going to be doing. But there's this other rule here, and this rule has a lambda on it. And remember how we had free jumps in NFAs? We sort of have free jumps in DFAs too. But in this case, we only have free jumps if this is what we see at the top of the stack. So this transition here is saying, look, whenever you want, if there's an X at the top of the stack, you can take this jump, okay, and do nothing. And that actually takes you to the accept state. But remember, you don't get to stay at the accept state. You don't win unless you've processed all your letters. So if we took this jump as our very first step before we process that first A, that would be all well and good, but we still have letters to process. So we'd say, well, that particular flow through this PDA doesn't work. So at this point, if we wanted to, we'd say, well, there's a free jump, but I need an X at the top of the stack, and there isn't one. So this is my only option. So I see a B. There is a Y at the top of the stack. So I'm going to follow this arrow, process my B, and it tells me after you follow the arrow, pop. So that Y at the top goes. And then there's only one transition that's at state 1 that we can take, right? And it says if you see a B and there's a Y at the top of the stack, pop. Unfortunately, we have the same number of B's as A, so we see a B, Y at the top of the stack, right? There's our Y at the top of the stack. So I'm going to process the B and pop, process the next B and pop, right? I keep taking this circle. Process the next B and pop, so I did this one again. And now the system says, well, if you are at state 1 and you feel like taking a free jump and there's an X at the top of the stack, you can take that free jump and end up at state 2. And I'm going to say, sure, I feel like doing that now. So I end up at state 2. My entire string has been processed. Therefore, I say the string AAAA, BBBB is in my language. If we want to just try one example of a string that's not in the language, okay, so let's try another string. Let's try a string that has more A's than B's, right? And again, like in NFA, there is non-determinism in here. You know, you just have to have one path through this that processes all the letters and ends up at an accept state, and you get to accept. So I'm going to take the path that works if there is one. Of course, there shouldn't be one for this. So here's my string to process. There's my stack with an X at the bottom, right? And I start at state 0. I see the letter A. There's an X at the top of the stack, so I push a Y. Now I see an A. There's a Y at the top of the stack, so I push a Y. Same thing again. Right, so we have our 3 Y's on there. Now I see the B. This isn't even an option because there's not an X at the top of the stack, but so I see a B. There's a Y at the top of the stack, so it says to pop. I end up at state 1. I see a B, Y, pop. Oops, that top one, this one still is in there. Right, that's still good. And now I'm stuck because I only have two options for transitions I can follow, right? The first option is if I see a B and there's a Y at the top of the stack. Well, I don't see any more letters, right? So that doesn't help me. Or I could take this free jump if there's an X at the top of the stack, but there is no X at the top of the stack. It's a Y. So I'm done. I finish. I have to finish at state 1, and it's not an accept state, so I don't accept this string. And you can see if you try and do it with another string that has more B's than A's, so if you try it with like AA, BBB, you'll see you also get stuck and there's no path through this. So this is indeed a PDA, a pushdown automaton, that recognizes the language A to the N, B to the N. And now you see we've talked about this whole lambda transition thing now, right? Lambdas are free jumps, except that you have to, it's a free jump as long as there is whatever happens to be specified at the top of the stack. Of course, we love our tuples. I've tried to color code this, right? This is so you can also represent an edge as a 5 tuple. So if we look, for example, at this red transition label here, we know that to go from 0 to 2, you can go to 0 to 2 on a lambda if you see an X at the top of the stack, and what you should do is a no-op, and this is saying, look, we've started at 0, we're going to 2, lambda X no-op, right? So the green is staying at 0, right? If you start at 0, end at 0, you have the letter A, you see an X, you should push a Y. For this kind of light blue, again from 0 to 0, if you see a 0, if you are at state 0, you see an A and a Y at the top of the stack, you should push a Y and then continue to state 0. This one looks like that, and I'm just asking you what should the 5 tuple be for the last two here. So let's do this first 5 tuple. Well, the first one here, this one is what I'm working on. You're starting at state 1, you are ending at state 1, and you see B, there's a Y at the top of the stack, then you pop. For this other transition here, let's do it in a different color, right? You are starting at state 1, you are ending at state 2. It's a free jump, a lambda, but you have to see an X there, and you do a no-op. And I've said this out loud, but now let's just see it in writing. A string is accepted by a PDA if there is some path, right? This is another non-deterministic. You may have to try a couple different paths. You can do it using the it's magic, I always take the right path approach that we talked about, or the try all paths and see if any of them work approach that we talked for regular languages, so that should be understandable. So a string is accepted by a PDA if there is some path from the start state to a final state that consumes all the letters of the string, right? That's the most important part, right? Otherwise, the string is rejected by the PDA. And of course, we talk about the language of a PDA is just the set of strings it accepts. It's just like when we were dealing with regular languages and NFAs. Now we're dealing with context-free languages and PDAs. So another definition for you. This is kind of a definition of do I have to use magic? If a PDA is deterministic, right, then there's at most one move possible from every state. So you don't have to take a magic jump ever, or use magic to guess which path to follow. It's always determined. It's deterministic. And if a PDA is not deterministic, then it's called non-deterministic. So here's my question for you. Take a look at the PDA in this image and tell me, is this PDA deterministic or non-deterministic? Right? Is there any state that has two possible moves where you're going to leave the state where you could have the same combination to do so? And the answer is it's actually non-deterministic, because if X is at the top of the stack, right, and A is the next letter, there's two choices. There's this one, which looks obvious if you're at state 0, of course, right? We're talking about from state 0. There are two choices from state 0. If you see an A and X is at the top of the stack, you could take this transition. But you could also say, oh, I'm going to do a free jump now because there's an X at the top of the stack, and I just won't process my A this time. So this PDA that I'm showing you here is non-deterministic, right? Because there are two possible options from at least one of the states. In this case, from state 0, there are two possible options. Now, one nice trick, if you do write out your 5 tuples, is it's pretty easy to tell if a PDA is non-deterministic just by looking at the 5 tuples. So, if either of these two things are true, it's non-deterministic. So, if you've got two 5 tuples that have the same first 3 components, then it's non-deterministic, right? And that makes sense because the first component is where you're starting, right? Let's look at this one for a second. Let's just look at the second line for 1 second, then we'll go back to the first line. So right here, this 0AX push Y, right, that represents this guy here, right? Let me maybe circle both of them. Okay, so this thing here is the 5 tuple for this particular transition from 0 to 0. And if I have another transition that starts at state 0 that sees the letter A, that happens if you see the letter A and there's an X at the top of the stack, that would make it non-deterministic, right? If I looked through my list of 5 tuples and one of them had the same 3 things at the beginning, it would be non-deterministic. But because of these free jumps, there's one other option, which is if they have the same first and third component, and one of the 5 tuples has lambda as the second component. And so that's what's going on here between these two, right? If we look, remember we said that from state 0, there's 2 options if you see the letter A and you have an X on the top of the stack, right? And we can see that here because since we do have a lambda in the second position, if we have any two 5 tuples that have the first and third thing the same, then we say again it's non-deterministic. So, you know, in our world of documenting everything, it's nice to be able to sort of write out a list of what are the steps that we did, what are the steps that we followed on our PDA. And like I say here, it's kind of like showing a derivation for a grammar, okay? But what we're going to do is we're just going to give a sequence of 3 tuples, and we're going to say, here's where I am right now, here's what's left over in the string, and here's what's on the stack for every single step that we do. So let me show you an example. And I'm sorry, this is a little bit messy, but what I'm trying to do is show you the computation for how do we say that the string AABB is accepted by this PDA. This is our old friend A to the N, B to the N. So let's step through and see what happens. Suppose we have the string AABB. I'll just draw a stack in here with an X at the bottom, right? This line here, the first line, says we start in state 0, right? Which makes sense. Our string has AABB, which it does, and the top of the stack is an X, which it is. And then after we process, after we take our first step, what are we going to do for our first step? Well, you and I both know that for our first step, what we're going to do is we are going to take this loop, right? So I see an A, and there's an X at the top of the stack, so I'm going to push a Y. So I'm going to get rid of that A, and I'll push a Y. This next line here says, now I'm back at state 0 again, but my string, that's the unprocessed part of my string, is ABB. Yep, look, ABB is all that's unprocessed, And what's on my stack from top to bottom? It's y then x. Look at that, y then x. Right? If I continue to process the string, what would our next move be? Well, our next move would be to follow this loop around, right? Because we have an A and there is a Y at the top of the stack. So we're going to do the push Y. So let's just do that. Process the A, push the Y, and I'll take that loop. So at this point, maybe I'll circle in purple just for fun. I am now still at state 0. The remaining unprocessed part of the string is BB. And if I look at my stack from top to bottom, it's Y, Y, X, Y, Y, X, right? Next move, we're going to process that B. Really, the only move we can take right now is this transition. So process the B, we see a Y at the top of the stack, so we'll pop. So we process this B. There's a Y at the top of the stack, which we pop. We've transitioned to state 1. And where are we now? Well, look, we are now in state 1. Yep. The remaining part of our string is just a B. That is true. And if we look at what's at the top of the stack, from top to bottom, YX, and sure enough, there's YX. Last step, almost. We're going to take that loop to process that last B, right? So we process this B. Because there's a Y at the top of the stack, we're allowed to take that transition, and we pop it. And now we are back to a state. We're still at state 1. Right? Lambda, there's nothing left to process. We have the empty string, and there's an X at the top of the stack, right? Or X is the entire stack, right? And the last thing that we do, of course, is we take that free jump. So we are going to follow the jump down to there to state 2. And that is a free jump on lambda. If you see an X at the top of the stack, do nothing, so we don't mess with that X at all. And our final step says, look at this, we end up at state 2 with lambda as the unprocessed part of the string. In other words, our string is totally processed and X is at the top of the stack. So this whole set of 3 tuples is a sequence that can let you recreate exactly how you successfully passed through, or unsuccessfully passed, I suppose, but really you're only going to use it for a successful computation, how you successfully passed through the PDA. All right, let's work through some more problems. This first problem asks us to find a PDA for all strings over the alphabet AB that have the same number of A's and B's. So we already did a grammar for that. Now it's asking us to do a PDA for this language, right? And what I'm going to do is I'm going to try and give you a feel for my thought process in this, okay? And so what I'm going to think about is I have to have the same number of A's and B's, but at any given time, I might have the same number, in which case I could accept, or I might have more A's, or I might have more B's, right? So what I'm going to do is I'm going to use the stack to keep track of whatever I have more of, okay? And so what I'm going to do is the following. Let's start, and let's say for starters, remember, if we see an X at the top of the stack, because of the way I've set this up, an X at the top of the stack means whatever we've processed, whether it's 0 letters or 50 letters, that we've seen the same number of A's and B's. So if I see an X, I'm going to have, at the top of the stack, I'm going to have a special free jump. At any time, if I want to, and I see an X at the top of the stack, I can jump to my magical accept state. And this is important because, of course, the empty string should be accepted, right? So if I get to state 1 and I don't have any letters to process, and so I take free jump with an X at the top of my stack, magic, I accept. Okay. And now let's talk about the other cases. There's a couple of possibilities, right? Let's suppose that everything is even. Okay. And if everything is even, right, so we have the same number of A's and B's so far. Maybe I'll write kind of a list, right? One option is we have same number of A's and B's have been processed so far, right? If that happens to be the case, then we're going to have an X at the top of our stack, okay? And if that's the case and we see an A, well, we know now we have more A's than B's, so we're going to start stuffing A's onto our stack to keep track of them. On the other hand, if we have an X at the top of our stack and we see a B next, then we'll say, okay, well, now we're going to use the stack to hold B's until we see some A's to get rid of them, okay? So when we start out, of course, we have the same number of A's and B's processed so far. So let's suppose, and of course when we start out there's an X at the top of the stack. So let's suppose when we start out we see an A and there's an X at the top of the stack. Then what I'm going to do is I'm going to push something that tells me, ooh, I have one more A than I do B's. So why don't we push, and I'm going to push a capital A. I could push whatever I wanted, but I'm going to push a capital A. Mostly because that's just easier for me to remember. So let me see if I can squidge this guy a little bit more so it's out of the way. All right, so what I'm going to do is, and if I see more A's after that, let's push more A's on the stack. So if I see a little A and there's a big A already at the top of the stack, I'll push another A. All right. So as long as I keep seeing A's and I have more A's than B's, I'm just going to pile up those A's. So, you know, maybe my stack has an X and then it'll have a bunch of A's on it, each one representing an extra A. At some point a B is going to come along, we hope, if we're going to accept this. And whenever I see a B, if there's an A at the top of the stack, I want to get rid of that A, right? So I'm just going to change color so it's a little bit more clear because I'm running out of space here a little bit. But so if I happen to see a B and there's an A at the top of the stack, I'm going to do a pop. I'm going to kind of process my B and at the same time get rid of one of those A's. And I'm going to keep doing that as long as there's an A at the top of the stack. So far what we've got in these three rules is if there's nothing on the stack, right, there's just the X, and you see an A, push an A. If there's already an A on the stack, that means I have more A's than B's. You see another one, push it. If there's already an A on the stack and I see a B, oh, hooray, finally we're equalizing a little bit, I will pop it. So that's kind of the first half, but that doesn't take into account any situations where we have more B's than A's at a given time in our string, right? So we need to essentially do the corresponding rules for the other side. So if it's even, so the number of A's and B's I've seen so far, I've processed so far is even, so there's an X at the top of my stack. If I see a B and there's an X at the top of my stack, let's push a capital B instead. So now we're using the stack to hold the extra B's, as it were, right, or to hold a record of how many extra B's there are. And I'm going to just change color to make it so they don't blend in so much, the rules with each other. Again, if I see a B and there's already a B on the stack, then I push another B, so I always keep track of how many. But if there's a B at the top of my stack, I'm just using another color to make it clear so that these things don't run into each other. If there's a B at my top of my stack but I see an A, well, hooray, I'm starting to even stuff out, so what I'm going to do is I'm going to do a pop just to get that off. So what I encourage you to do is copy out possibly a little bit more neatly. It's probably easier for you to write this neatly on paper than it is for me to write it here on my iPad. But copy out this PDA. Of course, you want to write start there, right? Copy out this PDA and test a couple of strings on it and make sure that when you test it, you can accept those strings that are that have the same number of A's. So you could try like the string AABB, same number of A's and B's, or ABBA, right? All of these should work, or AAABABBB. Does that work? And then try some that don't have the same number of A's and B's, right? Add, you know, an A onto the front of all these, or a B onto the front of all these. But I want you to just try this out and see how it's processed, because again, a lot of this is just kind of learning some of the tricks and understanding and really feeling in your gut, okay, I see how these things are processed, right? Okay, so let's get rid of all this mess and let's take a look at this. And oh yeah, now we're trying to find palindromes of odd length over AB. All right. So this is where a PDA really comes into its own. And this is where we really do have to use that kind of magical approach to drawing these things. There is just no way that we can do this problem deterministically. So let me tell you what I'm going to do, and then I'll draw it, and then I want you to check it. Okay? So what I'm going to do is the following. For any given palindrome that's an odd length, right? If you think about it for a minute, there's a bunch of letters. Then there's some letter I don't really care about, right? That could be an A or a B. And then I start repeating the letters backwards, right? So what I'm going to do is I'm going to have a couple of states. I'm going to have one state where all I'm doing is pushing the new letters as I see them, if they're the letters on the first half of the palindrome, onto the stack. Then when I get to the middle letter, how do I know when I get to the middle letter? Well, this is the non-determinism. It's kind of magic. I'll take a magic jump, and I don't really care if it's an A or a B. And then I'll start matching, and I'll say, there's my A, cross it off with that A, pop it off the stack. There's my B, pop this one off the stack. There's my A, pop this one off the stack. There's my B, pop this one off the stack, and so on. Okay? So that's what I'm going to do. I'm going to magically know where the first half of my string ends, and where there's that middle letter, and then where the second half ends. And again, this is, I mean, I don't expect you to be able to do this without seeing it at least once, right? That's why I'm going over it. But once I go over it, I want you to kind of understand it. And this is where the importance of really understanding those kind of magic jumps in NFA or in NFAs, or you just try every possibility and see if any of them work. If you prefer that approach in NFAs, you really need to understand how that works with regular languages, because I'm not going to spend a lot of time on it here. We spend a lot of time with regular languages. With these context-free languages, I'm just going to assume you understand that stuff. Okay, so let me actually show you what that PDA looks like. So let's get rid of this. So what I'm going to do is I'm going to have my start state. And I'm going to start by whatever I see for the first half of my palindrome, I'm going to push on the stack. So if I see an A and there's an X on the top of my stack, then I'm going to push. Now, I could push an A. It would make the most sense to push an A. I'm actually going to push, let's do a smiley face, just to emphasize to you that we can put whatever the heck we want on the stack. It's got to be a symbol. It can't be X because that's a special symbol. But beyond that, we can put whatever the heck we want on the stack. So whenever I see an A, I'm going to push a smiley face. And that's if there's an X on the top of the stack. And of course we need a second one, because once I've started, when I, whatever it is, if I see an X or I see a smiley face, or in fact if there's B's on there, I need to also push an A. So for the first half, I'm just going to push an A whenever I see pretty much anything, right? So I could also say, if there's an A and there's already a smiley face at the top of the stack, I'm also going to push a smiley face, right? And similarly, I'll do that for B. So if I see a B and there's an X at the top of the stack, well, I can't do smiley face. I need to come up with something else that represents a B. Maybe I'll just use a capital B because I'm getting lazy. And if I see a little b and there's a big B at the top of the stack, oops, I will push a B. These should all say push, right? Push a smiley. I was so excited about the smiley, I forgot to write push. And we'll push that B. Maybe I can shrink this just ever so slightly. Okay. Now, of course, I might not see just A's or just B's, right? This isn't the same as the other problem. So, you know, if I see an A and there's already a B on the stack, I also want to push a smiley, right? To say, oh, look, I found another A. So maybe I'll use another color here just so you can see it all in there. Though actually, let's fix this arrow. That's my start arrow, and I never labeled it. So if I see an A and there's a B at the top of the stack, I also just want to push another smiley face to indicate, boy, I saw another A. It's a smiley face, I know you can't tell. And similarly, down here, if I see a B and there's already an A on the stack, I'm going to push a B. Now, this is getting really, really messy, and you know, computer scientists, we all love our shortcuts, so I'm going to show you a shortcut notation for PDAs that make our lives much easier. What I'm going to do is I'm going to take this whole thing and shove it up in the corner, and let me just start from scratch again. Okay, so here's my start, state 1, and what I'm going to do is I'm going to write the following. If I see an A, no matter what's on the stack, and that's supposed to look like a question mark, I am going to push that smiley face. And if I see a B, no matter what's on the stack, I'm going to push the letter B. So my stack, you know, if my string started out as A, B, B, and then maybe my little middle letter is A, and then I have B, B, A, then I would end up with pushing for these first three. I would push a smiley face, oops, there's nothing at the bottom, smiley face, and then a B, and then a B. Right. Then when I see that middle letter, I'm going to transition to state 2. And for that middle letter, I'm just going to change colors again to make it a little bit easier to see. If I see an A, I don't really care what's on the stack. I'm going to do a no-op. And also, if I see a B, I don't really care what's on the stack. I'm going to do a no-op. Right? And then when I get to state 2, so now I'll process that A, I'm going to start doing the matching. So I will see this B, and I'm only going to pop it if I see another B. I see the B, I'll pop it if it's a B. See an A, only pop it if there's a smiley face. And if I'm left with an X, then I know I've got my odd palindrome, right? Okay, so at this point, if I'm at state 2, if I see an A, and there is a smiley face at the top of the stack, then I will pop because they match. And if I see a B, and there is a B at the top of the stack, then I will pop because they match. And finally, if I get to the end, right, so it's a free jump, so I can take it at any time, but if I see an X at the top of the stack, I'm going to do a no-op and go to state 3, right? And so again, what I want you to do is to take a look. Let me just cross this off because that was our kind of example, and I don't want you to get confused with our example here, but I don't think I can split it to shrink it. All right, and let me just get this guy way out of the way. So what I want you to do again is to just take this picture that we've drawn here, right, this PDA, and I want you to try a bunch of palindromes and make sure you can walk through them and you can see, oh, here's a palindrome of odd length, I see that this works. Here's another palindrome of odd length, I see it works. Here's a string that is maybe a palindrome of even length, it doesn't work. Or here's a string that's not a palindrome of any sort, it doesn't work. I don't end up And remember, we only accept if you end up at an accept state and you've processed all the letters in your string. That's the key. So I really want you to try and see if you can try out this. Just test this PDA on some examples and see if it works. Or rather, convince yourself that it works. Okay, so let me just clean up the screen a little bit. And let's do one more problem. And this problem says, find a deterministic PDA that accepts by final state, right? So this is in the book, it says, find a deterministic PDA that accepts by final state. Well, all of our PDAs accept by final state. That's how we're doing it. There are other ways, obviously, to represent PDAs, but for this class, we're just doing one that accepts if you get to the final state and you've processed your string for this language, a to the n, b to the 2n. Now, the tricky part here, you could do a to the n, b to the 2n, I hope. Well, maybe not at this point, but once you've seen it, it shouldn't be too bad. So what I'm going to do is I'm going to do it two ways. First, I'm going to do a PDA, which would be kind of my gut reaction to how to make a PDA for this, the easiest way to make a PDA. And then we're going to talk about why the PDA that I made is not deterministic, and then we'll have to figure out a better way. A to the n, b to the 2n, such that n is greater than or equal to 0, right? So the logic that I would use, the way I would think about this, if I were doing this, and I weren't worrying about deterministic, non-deterministic, is I would say, okay, well, every time, I need to keep track of how many A's I have, so I'm probably going to push A's on the stack. And I need to, for every A I push, I'm going to have to pop off a B, right? And so there's actually two ways I can do that. I could either kind of have a hack where whenever I see an A, I push two A's on, and then when I see a B, I just take them off one at a time. Or I can say, okay, for every time I push an A on, when I get to the B part, I'm going to have to pop two B's off for every A that I see. I'm going to do it the first way. So every time I see an A, I'm going to push two A's on my stack. Now, of course, we don't have a way to push two things on your stack in one step, but you can always do it in two steps. So what I'm going to do is the following. So just take a look. I'm going to say, here's my start, right? And I'm going to say, if you see an A, and there's an X on the stack, I'm going to push an A, but instead, and I'll push a capital A. Instead of a smiley face or whatever, I could push a lowercase a. I've decided I'm going to push a capital A. And go to state 2. So I'm not staying in state 1 right now. And what I'm going to do is state 2 is going to be my state, and I'm going to only go to state 2 if I've just seen an A, if I've just processed an A. And so what I'm going to do is the only thing I'm going to do in state 2 is I'm going to say, no matter what's up next, free jump, the only thing you can do is a free jump, and in fact, no matter what's on the stack, push another A, right? And so now every time I see one A in my string, I'm going to push one, and then I'm going to push another. I'm going to push one, and then I'm going to push another. And in fact, you know what? I need another rule that takes me from 1 to 2 that says, if I see, here, let me do it in blue. If I see an A, and there's already an A on the stack, push an A, right? And you know what, actually, if I get to state 2, I know there has to be an A on the stack, so I could do that. And the truth is that I could combine the two rules that transition from state 1 to state 2 with just a question mark here, right? But the basic idea is, if I see an A, if I'm in state 1 and I see an A, go to state 2 and push an A, right? No matter what's on the stack. And once I'm in state 2, the only way you can get out of state 2 is to go back to state 1 and push an A. So I'm going to keep doing this, pushing 2 A's at a time whenever I see 1 A, until I've got all my A's pressed. And then I'm going to have a transition to my deal with the bees scenario. And I could probably stick around at state 1, but I don't have enough space, so I'm going to go to state 3. So, if I see a bee, there darn well better be an A on the top of the stack, and I will pop. And that's going to be true as I hang out at state 3. If I see a B, there better be an A at the top of the stack, and I'll pop. So even though I have twice as many B's, I've pushed extra A's on to compensate for that. Right? And then when I am completely done and I'm ready to accept, I am going to transition to an accept state. And lambda, if I see X, I will do a no op. Okay. And this looks pretty good. It doesn't right now look non-deterministic to me. Right now it looks like a deterministic PDA, except we forgot something. We forgot a step, which is right now our PDA doesn't accept the empty string. It doesn't accept lambda. And in order to make it accept the empty string, the most obvious thing to do is to add a transition here that says if you see lambda and there's an X at the top of the stack, do a no op. But as soon as I do that, I make my PDA non-deterministic, because there's two rules, this one and this one, that could both happen if I'm at state 1 and I see the letter A. Right? I can choose between them. I have a non-deterministic PDA. So we need to think of another way to cope with this situation where I want to be able to accept the empty string, right? So step 1, before I keep going, before I go on with this, I want you to just copy out this PDA that I've drawn, right, and process a few strings through it. So yeah, it's non-deterministic. We didn't answer the problem that we were asked, but at least it is in fact a PDA that works. Maybe we'll try and do one. So let me just show you. I'm going to have to shrink this a little bit so I have some space to work. Let's see if this works. All right, so there's my PDA. And let's suppose that we see, let's suppose we see the string, let's do two. Let's do one that works and one that doesn't. We see AA, 1, 2, 3, 4 B's, right? We're going to start with our stack with an X at the bottom. And it would be legal for me to follow this, but then I'd get straight to state 4 and I'd still have things to process, so I wouldn't accept. So it wouldn't be in the language. So let's take the other option, which is I see an A and there's an X on the stack, this guy, so I'm going to push an A. So I process that, I push an A. Now I'm at state 2, and I have to take this free jump, which says no matter what, if you see an A at the top of the stack, just push another A. So I do that, and I don't consume any more letters. I process the second A here because I'm back at state 1, and I use this transition. I have an A. I see A on the stack, so I push an A. And then again, I'm at state 2 at this point, and the only way to get anywhere is to go back to state 1 and push another A, right? At this point, I see a B, and the only thing I can do to get out of 1 on a B is to take this transition, which says if I have a B and I see an A at the top of the stack, pop. So I will process that and pop. I'm now at state 3, and I don't see an X, so the only thing I can do is take this BA pop. So I process my B, I see the A at the top of the stack, I pop it. I'm going to do that again from state 3, and again from state 3. And now, finally, I'm in a situation where there's an X at the top of the stack, so I can take this guy. And in fact, that's the only legitimate move I can take out of state 3 now, So I end up in state 4, which is an accept state, and I have processed everything in my string. In contrast, if I had, let's say, the string A, B, 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 right? More B's than I should, right? Then what'll happen is I will be starting my stack with an X, but I will process this A, putting an A as the transition from state 1 to state 2, another A is the transition from 2 to back to 1. Then I'll process the B and go to state 3, popping this. I'll process the B, go to state 3 again, popping this. And then I'm in a situation where I'm at state 3, I see a B, but there's an X at the top of my stack, so I'm stuck because there's nowhere I can go from state 3 if I see a B and an X at the top of my stack. Right? I mean, I could take this jump if I want, right? I guess that's that's what I have to do is I end up at state 4, but now there's nothing I can do and I can't process that B, so it does fail. Okay? So this was all well and good, but again, remember that these two yellow states that I've circled, right, or transitions, make it a non-deterministic PDA, and this problem asked us for a deterministic PDA. So we need to have some way that we accept the empty string and yet still can deal with the fact that we need a deterministic PDA. And it turns out it's not going to be too hard. So let me just clean this up, and let's try and do it again deterministically now. So the thing that hung us up before was that lambda transition from the beginning where we saw an X, because we also need to deal with if we see an A and an X. So what I'm going to do is just another kind of a hack. I'm going to say, if you get to state 1 is now going to be an accept state. So I will accept the empty string just by virtue of arriving at state 1. And now what I'm going to do is I'm going to leave state 1 pretty much immediately, right? If I don't have the empty string, then what I'm going to do is, obviously if I don't have the empty string, the only way I can accept is if I see an A and an X, and I will push an A, right? And that'll take me, I guess, to state 2. And remember, we had this push 2 A's in a row. Well, we can do that right now just by saying, you know what? The only way I'm going to let you out of state 2 is I'm going to say there's only going to be one transition out of state 2, and it's going to be free jump if there's an A on the top of the stack, push an A, right? And that'll take us to state 3. And now what we'll do is so basically instead of looping back to state 1 when we saw our A's, so processing pushing A, we're going to do that between states 2 and 3. Okay. So what I'm going to do, I'm just going to change color so it's easier to read, is at this point, if I see another A I need to process and there's an A on the stack, there can't be an X because I've already processed 1, then I will push an A, and that'll send me to state 2, where the only way out of state 2 is if I see that lambda. Now, if I'm at state 3, sorry, not if I see that lambda, of course, is there's only one transition out of state 2, and it's just an automatic, you know, as long as there's an A on the top of the stack, you can push an A. So at some point, I'm going to see the letter B, and so I'm going to make another rule again. I'm going to change colors just so you can keep track of what's going on. That takes me to state 4 that says if I see a B and there's an A on the stack then what I will do is I will pop that A, and I'll do another loop here to keep up that process. If there's a B and I see an A, I will pop that A. Oops, I'll just say pop. Sorry, we just say pop. Not pop A, we just pop what's on the top of the stack. We just happen to know it's an A. And then finally, if we've processed everything again, I'm just changing color to make it easier to follow my picture here and see what I'm writing. We'll have an accept state here that says if I see an X at the top of the stack, at any time I can take this free jump and do a no-op to state 5. But notice now, yeah, I have a couple of lambda transitions in here, but in any given state, there's no way I have a choice, right? So this lambda transition here, this lambda transition here from 2 to 3 is the only transition from 2 to 3. So if I want to keep progressing, I need to take that one. And out of state 4, there are 2 options to get out of state 4. One option I can only take if there's an A at the top of the stack. The other option, which is my lambda option, I can only take if there's an X at the top of the stack. So if you look at this whole PDA that I've just drawn, it's a deterministic PDA. There's no magic, no nothing. No matter what you do, at any given time, you only have one potential choice. And of course, if there's too few A's and I end up seeing an X too early and I take this jump, I'll still have letters left in my string, so I won't be able to accept. I'll be in an accept state, but there'll still be letters in my string, so the string is not in my language. Okay, 2 more examples, and then quite a few more slides, but they'll be much quicker. Okay. So what we're going to do here is, it says construct a PDA that accepts the same language as this grammar, and again construct a PDA that accepts the same language as this grammar. So let's just look at this for a minute. This grammar looks to me like the language A to the N D B to the N such that N is an element of N, right? So you should look and confirm that you believe that. And now take a look at the second grammar, see if you can figure that out. It's one we've actually done before. I think this is that language. Well, I know it is. A to the N, B to the M, such that N and M are natural numbers, but also, all right, and N is greater than or equal to M. Okay? So these are the 2 languages that we need to make PDAs for. Okay, so let's rearrange a little bit. Let's push that way up there. Let's take this one and shrink it for now. Take this one and leave it nice and big because that's what we'll work on first. Okay, so A to the N, D, B to the N. All right, and nobody said it has to be non-deterministic, so we don't need to worry too much about this. So what we need is a bunch of A's and then the same number of B's. And so I hope your intuition is telling you that what you need to do is keep track of how many A's you have. And how would you keep track of how many A's you have? By pushing something on the stack every time you see an A. And then we'll see a D. That's actually, we may be able to do this deterministically because we have to see the D before we start popping the B's. Right? So I'm going to do something like this. I'm going to start, and every time I see an A, and I'm going to use a question mark here, no matter what's on the stack, it could be an X, or it could be whatever I'm about to decide to push, I'm going to push, and let's push, just for fun, let's push a Q, so you understand you can have anything that you want to use on the stack, except for X, right? X is the only symbol that we know means our kind of stack is almost empty symbol, so we don't want to use an X. But all right, so as many A's as I see, no matter what's on the stack, I'm going to push a Q. At some point, hopefully if I want to accept my string, I'm going to see the letter D. And when I see the letter D, there might be an X on the stack or there might be an A on the stack, but either way, I'm going to do nothing. I'm just going to keep moving. Because it's really when I see the B's that I want to pop. And if I'm at state 2, if I see a B, and I match that up with a Q that I pushed on the stack to keep track of my A's, then I will pop. And hopefully if I have the same number of A's and B's, I'll end up with an X, right? If I do have the same number of A's and B's, I'll end up with an X on the stack. And so then I can move with a lambda X no op to state 3 where I accept. So let's just do a quick look and see, is this a deterministic PDA or a non-deterministic PDA? If I'm at state 1, I can only take one choice, right? If I see an A, I have to take this choice. If I see a D, I have to take this choice. If I'm at state 2, again, only one choice, because if there's a Q on the stack at the top of the stack, I take this loop. If there's an X at the top of the stack, I take that one. So it looks like this is actually a deterministic PDA for this language. Again, now's a good time. Pause the video, copy this picture out, try and do it. Make sure that if you try some strings, right, so here are some strings that this PDA should accept. It should accept AAD, BB, and it should accept D, right? And 1, 2, 3, 4, and a D. 1, 2, 3, 4. Oops, that's an A, right? Not a D. On the other hand, it should not accept, I'll do them in red, AD, BB, and it should not accept AABB, right? These are no-goes, right? Because those strings are not of this form. Okay? So, test that. Try it. Make sure you understand that. Let me clean this up and we'll try the other one. Okay, so we did that one. Now it's time to do this one. So now we want to do all strings of A's and B's where there's A's first, then the B's, and but there's more A's than B's or the same number of A's as B's. So here are some strings that are good. AAABB or AAB, right? Or just A, right? And here are some strings that are no good. I will do them in red again. So let's see, we've got ABB is no good. A B by itself is no good, right? And so on. Okay, so what we need to do is we need, of course, to keep track of how many A's we have, and we need to make sure that we have the same number or fewer B's than A's. So let's do some drawing. And we need to make sure in the end that we accept the empty string, right? So in the previous example, we didn't have to accept the empty string because you had to have a D in it, but in this one we do. So let's see, let's take care of the empty string right away, and I'll just say I don't care if it's a deterministic or non-deterministic machine. If you want to at any time, you can take this lambda jump, and if there's an X at the top of the stack, you can do a no-op. All right? So now we know that if you have the empty string, you just accept. And now let's deal with everything else. What I'm going to do is my standard, and I'll just switch colors again just so you can kind of keep track of the letters on here and see who goes with what. And let's just shrink that a little bit so we're not taking up quite so much space. Okay, so like I said, as if we see A's, we are going to push A's on the stack. So whether I see an X on the stack or I see, I'll just use A's on the stack this time, I'm going to push. So I will say A, comma, question mark, push A. All right. Eventually, I'm going to be at the point where I see some B's, right? And every time I see a B, I'm going to try and pop an A. Now we need to be careful because we don't want to let ourselves have more B's than A's. But I think we should be okay. So let's see. I think what we can do is we can say, all right, if I see a B and there's an A on the stack, I will pop it. All right. And at this point, if I process all the B's and there's still an A on the stack, I still want to accept, right? So I can have a jump here that says, a lambda jump that says, if there's an A on the stack, I can do a no-op. Now the question is, I think this might be right. I think this might be the whole thing. I just want to check and make sure that I'm not going to accept a string like ABB that has too many B's, right? So let's see what happens if I have ABB. Let's just trace that one. So let's suppose I have my stack with an X on the bottom of the stack. And let's just see what's possible when I see that first A. When I see that first A and I'm in state 1, there's two moves I could possibly make, right? One is I take state 1 and I transition to state 2 using this lambda, but then I'm stuck at state 2 and I haven't processed all my letters, so I don't accept, so that's okay. The other is I take this loop, so let's do that. So I process the A and I push an A. At this point I see a B. And there's an A at the top of my stack, so the only transition I can take out of state 1 is, oh no, there's an A at the top of my stack, so I could take this transition or this one. If I take this transition down to state 2 at this point, well, I still have unprocessed letters, so I don't accept, so that's good. So I'll take this one, B, comma, A, pop. So I will process my B, and I'll pop. And now I have another B, and I'm at state 1 still. So I have a B, and there's an X at the top of the stack. So this loop doesn't work for me. This loop doesn't work for me. The only transition, and this one doesn't work for me because I don't have an A. The only transition that works for me out of state 1 is this lambda X no-op. So I could take this, but then I end up at state 2 with one letter still to process, and I don't accept. So I think this is good. I think this works. I think this is my PDA for this language here. Heads up, we are going to be skipping some of the material in the textbook that talks about PDAs. We're going to skip the section on equivalent forms of acceptance. What you actually just need to know is that you can describe a PDA in a bunch of different ways, and that's equivalent to the model that we're using. So you could talk about a PDA that doesn't have any accept states, but that accepts if the stack is empty, right? And the other thing you need to know is the set of languages that are context-free is exactly the same set of languages accepted by PDAs. So just like when we were talking about DFAs and NFAs and regular languages, they were all kind of equivalent. PDAs, languages that can be accepted by a PDA, same set as the languages that are context-free. And we're not going to do it, but you won't be shocked to hear there are algorithms that'll turn a PDA into a context-free grammar and algorithms that'll turn a CFG, a context-free grammar, into a PDA, just like we did turning the regular expressions into NFAs and NFAs into regular expressions. Now this next fact is a little bit more interesting, I think, okay? So, and again, I do want you to memorize it, but it's interesting, so it should be easy to memorize, right? There are some context-free languages that require you to make a non-deterministic PDA to accept them, right? You can't have a deterministic PDA that will accept them. So this is a little bit different, right? Because when we were talking regular languages, you could always draw a DFA for a regular language, no matter what, right? You have a regular language, there's a DFA you can draw for it. There's also an NFA, but there's definitely a DFA. Now that we are in the world of context-free languages, There are some context-free languages that absolutely require that you have a non-deterministic PDA to accept them, right? And remember, again, our definition of what's deterministic versus non-deterministic, right? We've been kind of looking at this. So just to say it again another way, the set of languages accepted by NFA is exactly the same as the set of languages accepted by DFAs. They are exactly the same, but there are more languages that are accepted by non-deterministic PDAs than there are accepted by deterministic PDAs. And furthermore, the deterministic PDAs, the set of languages accepted by deterministic PDAs, are a subset, right? That set of languages is a subset of the set of languages accepted by the non-deterministic, right? So if you can do it in deterministic, you can always do it in non-deterministic. Because you can always just add an extra lambda transition that with the non-deterministic one you never take, right? But if you have a non-deterministic PDA for something, you might not be able to make a deterministic one for it. You might, but you might not. Now, it's tricky to prove this, and your book doesn't even prove this, okay? But let's just talk about one example language that's only accepted by a non-deterministic PDA. And you may have already guessed, it's a language that we've looked at similar languages recently. And it is, in fact, the set of even palindromes over the alphabet AB, okay? And in fact, I think that the set of odd palindromes over the alphabet AB is also has to be non-deterministic. You can't do it deterministically, but I wanted to show you even palindromes, a PDA for it, since I'd already shown you a PDA for odd palindromes. And isn't this a beautiful, neat PDA, unlike some of the ones I've been drawing for you by hand? But, you can see what's going on in this PDA, right? Which is that whenever I see an A, I push an A. I chose to use a lowercase a here. Whenever I see a B, I push a B. I take a magic free jump no matter what's on the stack, and then I match A's to A's and B's to B's. And I take this magic free jump to get to my accept state. And the key thing here is, when do I take this jump? When do I stop pushing letters onto my stack because I'm processing the first half of my string and start popping letters off? And the answer is you can't know ahead of time. There's no way to know unless somebody told you how long the string is, which we haven't said. So it turns out that the set of even palindromes over the alphabet AB, and in fact the set of odd palindromes over the alphabet AB, both of those languages, you can only draw a non-deterministic PDA for them. You cannot draw a PDA for them that is deterministic. Go for it. Try. Think about it for a little bit. There's just no way to do it. These languages are context-free. They're both context-free. There is a PDA for both of them. We've seen PDAs for both of them now. It just happens that both of those PDAs have to be non-deterministic. You cannot do it with a deterministic PDA. And here's an extra slide that basically says what I just said, right? You can't make this PDA without this big purple link in the middle here, right? There's no way of knowing, is your letter in the first half of the string or the second half of the string. And that's what makes this require a non-deterministic PDA. And finally, two more facts that I want you to know, because I don't want you to finish taking foundations and say, boy, Dr. K never told me that. But on the other hand, I don't really think it's so important that we spend so much time on this. Okay? So the first thing is, if you have a context-free language that does not contain lambda, so you have a language where lambda is not a legal string in that language, lambda is not a part of that language, then you can generate it using a context-free grammar that doesn't contain lambda. And your book has an algorithm on how to do it. If you're interested, go look at the algorithm. If you're not interested, just remember this fact. And finally, you might hear people talking about putting their context-free grammars into Chomsky normal form. Okay? And Chomsky normal form is, just like we talked about regular grammars, which have a particular way you have to draw them, and you can have a language that is regular that's presented using a grammar that is not regular, right? If you have multiple non-terminals in a row, it's a non-regular, it's not a regular grammar, even though it might be a regular language. So for example, suppose I have the grammar A goes to BC, B goes to the letter B, C goes to the letter C, right? If this is my grammar, that is the language that only has one string, the string BC, right? So, you know, I can definitely make an NFA for this. This is definitely a regular language, but this grammar is not a regular grammar because we have two non-terminals on the right-hand side of this expression, okay? All right, so let's just get rid of this stuff. But if you have a context-free language, you can put it into a context-free grammar that's in Chomsky normal form, where these are the only production rules that you can have, right? Production rules of this form, right? Either you have a non-terminal going to a single terminal, a non-terminal going to a pair of non-terminals, and you are allowed to have the start terminal and start symbol, and only the start symbol go to lambda. Okay, and that's Chomsky normal form. And Chomsky normal form turns out to be useful if you want to write some proofs about grammars. If you say, all right, let me start by saying my grammar is in Chomsky normal form, that just reduces the number of things you need to prove. And so it does make things easier. And it's useful to be aware that Chomsky normal form exists and to know what it looks like, but we're not going to use it specifically in this class. So, you know, this was a really long lecture. There's a lot of material in here. Make sure you go back, look it over, rewatch pieces that might not be completely there, and do all the homework problems and make sure you really understand them.